Alright, so hello world, here we are, here we go, welcome. I have another programming question for the world, and let's go ahead and tweet out I don't think I get the link to the video until I'm actually streaming it, so that's why I'm sort of doing this in every video. Copy link location, there we go. Should do it. Okay, and now we can get into the video. Sweet, so I think that worked out pretty well. All right, write an efficient algorithm that searches for a value in an m by n matrix. This matrix has the following properties. Oh, you know what, let me close the other window. Integers in each row are sorted in ascending from left to right. Integers in each column are sorted in ascending from top to bottom. So each row is sorted left to right, and then each column is also sorted top to bottom. So pretty interesting question. I've seen this question before. I believe you can do this in O of m. If you could do log of m plus log of n time, logarithmic in m plus logarithmic in n. And the way to do it though is challenging. So obviously the simplest way to do this would be what they call just a plain old exhaustive search, right? And that would be O of m times n, right? O of m times O of n, or O of m, or O of quantity m times n. And that's exhaustive. That's a naive approach. So we want something better than that. Then another less naive approach would be to say, search each column and use a binary search on each column, or use a binary search on each row, and that would give you O of m times log n, or O of n times log m, whichever one's smaller. That's also sort of a relatively straightforward or naive approach. However, a slightly more nuanced and let's say, slightly more nuanced, subtle, and efficient approach would be. Now, I actually don't remember how to do this. I've seen this problem before as well on another website, but I don't remember the answer exactly, so I'll have to think about it a little bit. So what I want to say is you can actually start you can sort of do a binary search on the middle row, and what you can do is realize, okay, if the element is not here, then all of the elements below it are greater, and all of the elements to the right are greater. No, that's not necessarily true. Everything below this, well, you know what? Just thinking, like, if you searched a row, what could you eliminate from there? Well, I want to say something like, you can search this row to sort of find, I guess, where the element would be, and then you know that the element has got to be, I guess that means that the element has to be in one of these two columns, and then you can do a binary search on these two columns, something like that. I don't know if that's true. I don't know if that makes sense. I don't know, like, let's use an example. So like target is 5, right? So 5, we would search, 5 is between 4 and 7. So if it's between 4 and 7, that means that it could be in these two columns, these two rows, or these two columns. But it couldn't be beyond that, right? Because if is that true? Because no, I don't think that's true. I want to say something like all of the values that we're going to see down here are all at least as large as this upper bound. And then everything to the right is at least as large as that. So if this is an upper bound, right, it's not the value, so it must be larger than the value, then everything to the right and below, to the right and below is eliminated. And if this is a lower bound, then everything above it and to the left is also eliminated, because everything above it is smaller, and everything to the left and above everything to the left of those are smaller, and then everything to the left of this is smaller. So if you find a lower bound, everything above and to the left is eliminated, and if you find an upper bound, everything to the right and below is eliminated. Now, that's kind of interesting. However, that means it still could technically be in this region. Like you could have a 5 here, right? Even if you know, if you put like make these put zeros in all of these numbers, right? And then make the numbers in such a way where like you're searching 50 instead of 5. You have more numbers to work with, and then you can sort of extend the range here, so that way 50 could be like down here, and then 51 could be here, and then all the numbers between 40 and 51 could be here, and then all the numbers, you know, just subtract 1 from each of those numbers to put them here. And that would mean that, yeah, you could still have it in this row. Excuse me. So I think what you're going to want to do then is binary search on the middle row, and then that eliminates, you know, then you eliminate sort of a large portion of the top left, a large portion of the right, the bottom right, and then the rows that are left over, you can, I guess you could binary search on those too. Like you just split the, you know, you sort of do a search on this, you know, search on this row, I guess. And then you're looking for 5, right? So actually you would find it on this row. Here your search would eliminate these rows and these, like these values. And obviously, once you get down to 1 or 2 rows or columns, you can just, well, yeah, actually, so you search for 5 here, it goes right off the edge. You would eliminate this, and then you would search here, eliminate that too. So this would be an upper bound. No, excuse me. There would be no lower bound. This would just be an upper bound. This is already eliminated. You know, I think I'm doing this wrong. I'm not sure if it's O of m log m and O of log n, because the problem with this approach even would be, if you try to do it logarithmically, is that you also have a problem of actually, I'm kind of wondering if there's like, there's a few things to think about here. Actually, I don't know, man. Huh. I'm wondering if I should just do O of m plus n. That's actually better than O of m times n, and it's better than O of m log n and O of n log m. O of m plus n. It's sort of linear in terms of the length of the matrix. That's pretty good. I don't know if you need to do it in logarithmic time on O of log m plus log n. Huh. Gee. I don't know. The O of the solution that I was just describing, the kind of binary search. The problem with that is, yeah, you would eliminate, like, you could eliminate the part of the array to search, but then you actually have to program that, by the way, which would be like, you know, you search here and you say, okay, don't look at this column and don't look at these rows, but all the values, you know, you sort of like how are you gonna search this array and know not to search here, right? Something like that. Like, I'm not sure how to, not even sure how you would implement that or think about that. I don't think, it leads me to believe it's not on the right track. I don't know. I don't even know where to begin with that. That's like kind of complicated. And the problem that I'm thinking is that, like, you would need to keep track of all the things that you've eliminated, which I think is going to end up pushing you into an O of m plus n solution anyway. Like, you have, for each row, you'd have a pair of like values that you're skipping over, and then you might even be in a situation where, I don't know, you've got like, excuse me, sort of like a square of things eliminated or something. I don't know, you could, or like, you know, you have 4 elements here and then 4 elements there, and then somehow you have to know to just search for these two. Or even like this element, this element, this element eliminated, right? For each row and column, you have kind of like it's like you'd have an array of limited elements to not look at. So it's kind of funky. I don't know about all that. I also want to say something like, what if you just consider eliminating rows to the right and down, and just search for upper bounds alone, and forget about searching for the lower bound. So, you know, so if you don't find 5, but you find 7, so you eliminate all these rows, these columns really, and then you eliminate also the rows that are underneath as well. Or, yeah, the rows that are, no, you wouldn't eliminate the rows. It's really the columns. If you search it from the top, you'd eliminate all these columns. And then I guess you eliminate, then you search, if you search down the column, then you would eliminate the, that's another problem too, is you actually have to, well, you can search the column, it's just iterating over the column is a little funky. I guess I'd probably write rewrite the binary search from that upper bound binary search in order to iterate over the column instead of iterating over the row. You could write an iterator and then still employ the same algorithm, subroutine, but I don't think that's worth it to have a column iterator. I mean, maybe it is. It is worthwhile to just write a quick column iterator struct. But right, then you would. I guess you would binary search the top row, eliminate a whole bunch of columns to the right, and then binary search over the element that came just before it. Obviously, if you binary searched as the first element, then you're done, right? That eliminates everything. You just terminate early. But if you get like, it's okay, so you have this 4 that comes beforehand. Now you binary search down on the column, and you'd actually find the 5 right there. But let's say this was like 6, 7, 8, 9, right? And 5 wasn't here. You would see 6, and now you eliminate all of the rows that are underneath, as well as that column, right? Or rather, yeah, you eliminate all the rows underneath, and then you would say, okay, now you have then you have now the deal is this isn't I don't know, you gotta go to the first column. Yeah, if you go to the first row, eliminate all those columns, go to the first column, and now you can eliminate all these rows, right? So you eliminate these 2 rows, and then you go back to the first row. Oh no. Can you? I mean, that's great. You get rid of all the columns and all the rows, but then what? You guess you search what's left. No. Huh. You want to do something that involves cutting the matrix into like half, more or less, or some significant fraction. Yeah, you can't. When you search on the first column and the first row, so actually you could eliminate the first row and all of the columns to the to the right, and including, right, because you know it's not there, so you could eliminate the first row, and then you can look at the first column and search, and then you eliminate the first column and also all of these rows beneath. And I guess in theory you could just keep searching row by row and column by column. Although that kind of defeats the purpose, right? Because if you search row by row, there's really no point in even eliminating anything, right? This doesn't really... Okay, so you search the first row, eliminate some portion of the columns, and then you search the first column and the first row and some columns, and then you eliminate the first column and some rows. But then yeah, you're still just alternating between rows and columns. Ideally, what you'd want to do is if you pick the middle row, you're pretty much always going to eliminate half of the matrix, right? You eliminate all of this stuff, you eliminate the middle row, and you eliminate all of this stuff. Or excuse me, sorry, yeah, all of this stuff. And then I guess you'd start in the middle of, oh, you know what you can do? Ah, I got it. There you go. Once you've eliminated these things, you have a recursive subroutine. Ah, that's clever. I like that a lot. You have a recursive subroutine that operates on the matrices that are left over. Aha, which there will be two submatrices that are about half the size each, a quarter the size each, and you recurse on those two. Oh, I like that a lot. I like that approach a lot. I think that's really clever, right? And then all you have to do though is you have the initial matrix here, and you have a basically I guess it would be the what do you need for the rectangle? You need the number of rows, the number of columns, and then the starting top left. So the sort of, yeah, I guess a row column pair at the top, or just row column, and then number of rows, number of rows, number of columns, right? So here you would have 2 rows, excuse me, 1 column, and it starts at column 0, excuse me, and row 0, 1, 2, 3, row 3, column 0. And then the other side, you'd have 3 rows, 3 columns, and the first row, the 0th row, and the 0, 1, 2 second column, right? And obviously the initial state would be 0th column, 0th row, and m by n rows. And right, and you just take the middle row each time, and you say, okay, perform the binary search, and you say, okay, we don't find anything in any of these like we don't find anything here. So now we would eliminate this entire bottom half, these 2 rows, and recurse here. And there is no second row to recurse on. I have to write that correctly, so that way I could probably just write the routine, so that way, like, if you're given like 0 rows and 0 columns or something, 0 rows or 0 columns, it doesn't matter what the starting point is. You just terminate early, right? You just sort of have like a return false, I guess. And then yeah, so this would be another binary search on this row, these 2 rows, this row, and this would return false. And then on the other side of the depth first search is really what it becomes. You have these 2 elements to search. Oh no, excuse me. Eliminate this and these, and then eliminate these, and you would search on this thing. And I guess you could do. Yeah, it is something of a binary search. It's pretty interesting binary search. But a recursive search I like more so. And then you have 5. You'd say you'd find this upper bound. So you eliminate these, and eliminate also this row. And you sort of have this matrix left over. You actually find it here. You also have it down here. Really interesting. I don't know. Okay, I like that. I want to try that. I think it's O of m log m by n, which is O of log m by n. Yeah, because you do split the matrix into into 2 pieces. When you go to the middle row, you don't know what percentage will be eliminated. It doesn't matter. Any element you pick, you're going to remove about half of the array of the matrix, because all of the columns to the right and all the elements to the right and below of that whole section will be eliminated, and all of the the other elements above will stay, and then all the elements to the left of that point and above are also all eliminated, because they're all the ones to the left are too small, all the ones to the right are too big. So you always remove roughly half, right? So you would remove all these elements and these elements if it's between here. If it's between here, it's then these ones and these ones are left, and then these ones are all eliminated. Basically, there'd be 2 elements here that you keep, that on the other side you would lose. Yeah. Yeah, you can get. You just have to guarantee that you have half as many elements to go through each time, which is true. So that's a really interesting approach. I like that a lot. I want to try that. See if I can get that to work. See if I can code that up correctly. This took me a while. If I had this in an interview, I probably wouldn't have thought of that, and I'm not sure if it would be this good either. Don't think it would be really that good. Like it would take me a while to think of it, and it would also take me a while to like code it properly. Okay, so recursive search, and we'll say something like this. We want to give it the function, and we're going to have a bunch of different what do you want to call that? What you would call that? A bunch of different input variables. So we would have, we'll do a pair of int, or actually we'll do int row, row, or s row, s column, num rows, num columns, and then, actually I think that's all we need. I don't think we need more than that. And we'll have just a sanity check. If not, matrix if empty, or return false. N rows are just, we do n rows is equal to matrix dot size and the number of columns, matrix of 0 dot size, right? So you have the rows, the columns, the starting row, starting column, number of rows, number of columns, the matrix, and we're going to say, okay, select row in the middle, select middle row. So we want to say int count, we're going to call that. That's going to be the starting row, it's going to be the number of rows over 2. And then we say int step is going to be starting row plus the count. Then we say perform binary search to find the midpoint, or find the find the upper bound in the middle row, in the target row. So perform binary search to find the upper bound in the middle row of the matrix. Step, and we'll say step row, and also auto step column is going to be matrix of step row begin plus the count, or rather, we'll count row and count column. So, okay. Step column is going to be the step row plus the step column. Right. And now we're going to say that's sort of the, I guess, the middle. Okay. Perform binary search to find the upper bound in the middle row of the matrix. Perform binary search to find the, you actually don't need step column. You can do, no, you can do it this way. Step row, step column. S column is what it should be. Yeah. We'll just say initial column. Right. Little confusing, but I think this is correct. So perform binary search to find the upper bound in the middle row of the matrix, for which are to the right and below are larger. Okay, so this is interesting. Upper bound is going to be it's greater than, but lower bound is greater than or equal to. So we want to use lower bound. We're going to use lower bound of initial column. And we're going to say matrix step row end. And the value is going to be the target. Say auto it, right? Say if it is equal to target, then we return true. Else, otherwise, we're going to return we want to say, so there's a few things here, right? If the, it could be if there's like some edge cases. So it is equal to okay, it is equal to matrix, so off the edge of the row equals matrix step row end. Off the right edge. Okay. Off the left edge of the row, otherwise. So we have three different return cases. So if we're off the right edge of the row, what we want to return is f of, we're going to say what the starting column, the starting row is going to be. So So there's some starting row, starting column, top left corner, and there's a number of rows, number of columns, and now we're going to break that into two matrices. If you take the int, so we'll call it new starting row, so if we go, let's actually do it this way. I have a better idea. Let's do it this way. New starting row, there's a right matrix and there's a left matrix, right? On the right side, we're going to say the new starting row it doesn't change. Yeah, the new starting row doesn't change. On the left side, though, the new starting row does change. It's actually going to be this count row plus the starting row plus the count row. Right, if you just look at a matrix and you sort of remove the middle row, the top and all the elements, the top and the left, and all the elements, the right and below. And there's some midpoint where this happens. The starting row for these two matrices, the top right matrix is going to have the starting row is the same, doesn't change, and the bottom left starting matrix though is going to be that starting matrix plus that middle matrix. So it's actually going to be the step row plus 1. And there's another issue here. We'll get to that. Yeah, that'll actually be in this an edge case here. If we sort of go off the bottom row or above the top row, or off the right edge or off the left edge. Okay, I think I can actually handle those cases, all of that in one shot. In one case, I'll take a look at that in a minute. So but the left starting row is going to be that step row plus 1. Then the new starting column on the right side. The starting column on the right side is actually going to be above the point that you found, this lower bound, this iterator. So you take this iterator and subtract it from matrix step row begin, or the initial column, and you get that distance. That should give you the index for the column for the right side, and then the new starting column for the left side doesn't change, right? Left side doesn't change, that column is the same. And then the number of rows and number of columns is going to be the difference. So n new number of rows, number of rows on the right side. The number of rows on the right side is going to be, I think it's going to be that step, right? It's going to be the count rows. Should be -1, I think. Because you've eliminated that middle row. And then new n rows left is going to be the number of rows minus the rows on the right side. And the new column, number of columns on the right side is going to be similar. That's going to be the difference from the end. Now, it's actually not to the end. I'm sorry, this shouldn't go to the end. This is actually going to be, it shouldn't go all the way to the end. This should go to initial column plus initial column plus the number of columns. Yeah, it's a slight nuance there, but that's what that should be. A little confusing, but yeah. You don't want to use end here. This should actually be initial columns plus number of columns. Minus, should be the other way around too, by the way. The initial column minus the, oh no, that's fine. No, it is, yeah. This is, the number of columns on the right side is going to be the difference between this initial columns plus number of columns minus the iterator, right? So the initial column plus the number of columns, and then the iterator is somewhere in between there. And that's how many columns will be on the right side. And then the number of columns on the left side. This is kind of a lot to do during an interview. This is like a lot of thinking going on here. The new number of columns on the left side is going to be, the number of columns doesn't change. The number of rows, you do lose one row. But that's going to be the other side, which is actually the iterator minus the initial column. Yeah. I want to say this is also, this is a little confusing, this part, but the initial column plus the number of columns takes you all the way to the end. And then you subtract where the iterator is. That tells you how many columns. I think there's another way to do this too, which would be like, yeah, I mean, yeah, that's fine. You subtract the iterator because you actually should add one too, I think, here as well. No, you already add one when you add the columns. Do you? Hold on. If the initial column is 0 and the number of columns is 1, 2, 3, 4, 5, so 5 minus, let's say the iterator goes to 0, 1, so 5 minus 1 is 4, 1, 2, 3, 4. Yeah, that's, I'm just thinking like if we were searching here, fine, we say initial column is 1, number of columns is 5. Where does the iterator end up? It's also supposed to be, oh, this is so confusing. I don't think this is right the way I'm thinking about this, the way I'm doing this. It seems simple enough, but it's actually kind of complicated, kind of confusing. So also this iterator minus the initial column is also kind of confusing because there's kind of like an offset here. Well, I think that's right, actually, initial column. Yeah, I think that's okay. This is also -1, by the way. The new rows on the right side, it's going to be the count rows -1. It's not just count rows -1, it's the... Ah, that's annoying too. Gosh. Ah, this is so awkward. Ah, there's got to be a way to think about this. It's simple. No. All right, let's redo the whole thing. So, let's start with the starting row, starting column on the right side, and then starting row, starting column on the left side. Same thing. Number of rows, number of columns on the... This is definitely not computing in a simple way. The new starting row on the right side is got to be that iterator, where that iterator is. Remove the beginning part of that row, and that should give you the index. Yeah, 0 index. So that should just be iterator minus matrix step row dot begin. Right? Then that's the starting row. No, excuse me, that's the starting column. I'm sorry, that's the starting column. The starting row doesn't change, whatever the original starting row was. That's it. The number of rows is going to be it's not half, it's actually going to be all the rows from the starting point. So from the starting row plus the count row, which is the step row, really, start row plus step row. So yeah, let's just say starting row plus the count row minus 1. That's the number of columns minus the starting row, which is just count row plus 1. Okay, that's confusing too, because there's an offset that figures out where the starting point is for the rows. That's the starting row, and then you want to you have the count row away from the start row is the index of the row that you just worked on. You get rid of that row, so it's -1, and then you also have all the rows between the starting row. So the counting the number between starting row and starting row plus count row, you would have count row. I actually think there's not a -1 here. Starting row index plus, so it's actually starting row plus count. It's actually the number of rows. Yeah, okay, that's so confusing. But it's actually the count row. No, I think it's -1 though, because there's 10 rows. Count row is 5, 0, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 rows, 1, 2, 3, 4, 5. That's the 6 rows. 6 ro you do 6 minus 0 plus 1. Or it's 5, yeah, the 5th index. 5 minus 0 plus 1 is 6 rows. But you eliminated one of those rows. So you subtract 1. Which gives you 5. That's really confusing too. Ten rows, index 5. I want to say, yeah, if they're not 0 index, that's a confusing thing. Huh. So there's 6 and 4. Why? No, if you have 10 rows, you have an index from 0 to 9. I want to say there should be a subtract 1 here because it's 0 index. Like that's a really confusing thing when you're dealing with a 0 index and you divide by 2 on the total number. What you really should be doing is that's something I always get confused on. How do they do it on the... Oh, this is taking a lot longer than it should. But this is why you practice, so this kind of stuff is not so... It takes so much time. Step is the count divided by 2. Count is the distance between the first and last. So that's kind of interesting. If you... And you iterate, you advance the iterator by that count. Yeah. So if you had 10 elements, right? So you have index from 0 to 9. The distance from 0 to 9 is 10. No, the distance from 0 to 9 is not 10. I think that's the difference here. That's kind of a pretty subtle but important difference. Okay, what does this do? Is that an algorithm? I don't remember. I think it's it's algorithm. No, numeric. Okay. Ooh. All right, sweet. So that does what I thought I would do. Okay. Now what I want to say is this distance between test.begin and test.end minus 1, that is interesting. So this is 9, it should be. Yeah, that's what I thought. Okay. So if you do this divided by 2, you actually get 4, not 5. And if you print add this distance to the beginning, you're going to get 0, 1, 2, 3, 4. You'll get 4 instead of 5. Being instead of beginning. And it would help that we have a semicolon there, or colon there. Yes, so that is it's a subtle difference, but a very important and significant difference between the distance between test.begin and test.end minus 1. Even though there's 10 elements, it's 0 through 9 indexed. That distance is considered to be 9. In other words, you increment 9 times to get from A to B. That's a very subtle but important difference, because what I was just about to do is I was about to say the midpoint was just halfway, which is not what we want. We actually want the, if you add to, if you the distance you increment, right? To get from 0 to 9, it's actually going to be, you can just subtract. We just have to subtract 1. It doesn't make such a big difference, but it's a big deal, but it's not too bad. Yeah, so very subtle thing, but important. So okay, yeah, very subtle thing, but important. So now we want. Okay, so back to the logic that we have here. So now actually count row is the right amount. Now this should be the right amount. So if we had 10 rows, we would do the floor of 9 divided by 2, which is 4. And so we would add add 4 rows to the index, the current index, and that would actually put you at the 5th row, right? The first row you add 4, it goes 4 rows down. If we had and the 5th row, the number of rows that we added to the original row is the number of rows that's going to be in the first matrix, right? Because it's basically, if you just imagine removing the first row, right? Because it's the number of iterations that we need to, number of steps we need to take to get to the right spot from where we are, but not including where we are as a row, right? So if you just imagine, sort of taking those steps backwards, because now we're eliminating the row that we're at. So that's exactly, should be count row, number of rows. Pretty interesting, really important. And then if we had 9 rows, and let's say then we would do 4, it would still be 4, so we would still be at the 5th spot, and so there'd be 5 rows at the top and 4 rows at the bottom, and then you'd still be in the same spot. You'd eliminate the 5th row and still have 4 at the top, right? Really subtle thing, but really important. And actually, the number of rows on the left side is the same thing, right? The same reasons. same thing for the same reasons. You would have, no, actually not exactly. No, not exactly. It's actually the number of rows minus the count rows, minus 1. Yeah, that's on the other side. So the reason why you'd want to do this for the left side is because the left and the right side might not have the same amount if the number of rows is not an odd number. Yeah, the number of rows is an odd number, then you have like, like if it's a 9, you'd have 8 divided by 2 is 4, and so both of these would be 4, because this would be half of the number of rows, and this would be half of the number of rows minus 1. So this would just be number of rows minus 1 divided by 2, which is what this value is. Yeah, it's a little confusing, but if it's not even, if it's not odd, if it's even, then this is sort of you want these two things to add up to the number of rows minus 1, right, where you eliminate the middle row. So that's okay. Yeah. Anyway, so right, so the number of columns has a similar kind of a formula where we say that we did that binary search to find out at which point is sort of the starting column, and everything to the, not everything to the right of that is the starting column. It's, the thing about that is that tells you how many columns were eliminated to the left of it and all the columns left over. You could do it that way. You could do the number of columns to the left so the left matrix would be that index, that iterator where you got, right, some number. Everything to the left of it is, not everything, but everything to the left of it minus the initial column plus 1. So minus the starting column plus 1. I think that's actually it. It's just, that's some iterator pointing to some index, and there's some starting column. And if you subtract, I don't know, let's say it's 5, right? The 6th element, and this is 0. 6 minus 0 is 6. The element itself is not included in the columns on the left side. So you want to subtract 1 for the element itself. Yeah, 6 minus 0 is 6. And that's 5 columns. The fourth index is the number of columns. It's just the number of columns, right? So I think it's actually as simple as that. And you just have to subtract the matrix begin, which is, we'll just call that index, or row index, or just, yeah, index. Being instead of begin. As index. This seems really bad to do during an interview. This seems like a lot of like calculations and stuff that are just way more involved than like is reasonable. Like it's pretty involved. You know, I don't really like this that much. This is kind of awkward. So yeah, so the number of columns to the left is going to be that index minus the starting column minus 1 every time, I believe. That's the number of columns on the left. The number of columns on the right is going to be the it's going to be the sort of the inverse of that. It's the number of columns minus the index plus the starting column plus 1. Basically, this negate this and add it here. Yeah, that's like the easiest way that I can understand that. Yeah, you want to do this in relative terms as much as you can. Alternatively, it's the starting column plus it's the number of columns though, right? It's the starting column plus the number of columns minus the I want to say you subtract the number of columns minus the index. But really it's going to be the starting columns plus the index, right? Starting column plus the index. Oh no, the in. Oh, this is really awkward. You take the starting column plus the number of columns. That gives you sort of the final index. Take that and subtract the index. Right, which is what you did. Which is what I did here. Yeah, starting column plus number of columns plus. Oh gosh. Subtract that index and add 1 because when you subtract that index, it's everything to the left, including that particular column. But we are going to have that column in there. Yeah, super funky, really funky. The starting row on the left side the starting column on the left side stays the same, right? That doesn't change. The starting row on the left side though is going to be the count row plus 1, I believe. It's actually it's the starting row plus the count row plus 1. That's sort of the next index down. Yeah. Okay. Okay. All right. And what you're going to do is return f of, and you've got row, number of rows. So row, column, number of rows, number of columns. So new starting row left, new starting row, starting column left, and it's just going to be something like this. Or we'll just say, oh yeah, do it this way. So new starting row left. You know what you can do? You don't need new in front of all these, do you? You can just say, yeah, you really don't need that. That's also kind of awkward. And we don't need right either. We can get the idea. We can just say, oh, right. I wish I had thought about this in a way where, like I said, it's really simple, and I can kind of like easily realize what each of these values should be. Really simple formula, but no, these two and these two are kind of always going to be kind of complicated. Not these, this one, and I guess these two. I don't know. I think they're all kind of have that way about them. And then actually, so starting row L, starting column L, and then you have number of columns L. Is it row column, yeah. And number of columns L. I think it's just those 4. I think that's it. 1, 2, 3, 4, and then F always. And then you have the same thing going on here. Yeah, that's it. And it would just have an or in here. These are all on the right side. Now, you may have noticed something which is the boundaries. You would say something like if sanity check, if S row, starting row of, if the starting row is less than 0, or starting row is greater than the number of rows, or the number of rows is less than or equal to 0, and then the same thing on the other side, which is starting column is less than 0, or the starting column is greater than the number of columns, or greater than or equal to, these are 0 indexed, or the number of columns is less than or equal to 0. All these return false. Those all should occur in the case that like you have sort of quote unquote degenerate cases, then you'd have these things that could happen. They're not really degenerate cases, like the cases where you kind of go like, maybe I guess they're sort of like the end points, like sort of the end cases where you're sort of over or under, or like you're looking at a matrix that only has one row, and so when you search it, both the top and bottom matrices don't really exist, we'll say. So both just return false here. If you say if it is equal to initial column plus n columns, then we return false. Now, this means you went through the row. You don't actually want to return false here. You just say, if this is not equal to true, the problem with this is if this means that we didn't find it. If that's not the case, then we can check. Then we can check if this iterator is the target, and then we can return true. If this is true, we can't check this. If this is not true, but this is not true, right? So if this is true, then we want to check this. Yeah. So this is the every other case. I think we don't need this stuff then. That's what I want to say. Yeah, I think that simplifies things a bit. It doesn't really matter if this goes out of bounds, because you should end up in a position where, like, if this is the initial column plus the number of columns, this index, then what happens? I don't know if you end up with infinite loops or something, like I actually don't know what will happen with this. And forgive me, this is kind of involved, this approach. I'm definitely kind of messing around with this a little bit. I think it can be done this way though. The problem you have here is that this isn't really like, this doesn't break here, the sanity check. Because this is some index. It could be the end. It could be way off at the end. This is actually a number. Realistically, this could be 0, or this could be the initial column, or it could be the initial column plus n columns. In both of those cases, there should be some kind of degenerate thing that occurs. Sort of a degeneration, basically. That means that so when you execute on the middle row, the two matrices that result, if that middle row, or even if the middle row is like the top row, right, then obviously the right matrix doesn't exist at all. Or if the middle row, you execute on it and you end up all the way in the beginning, then you eliminate, excuse me, you actually still have a top and bottom matrix. If you end up all the way at the end, all the way off of the row, that's when you don't have a top and bottom matrix. Or if the matrices are such that like they only have one column or one row. Excuse me. Or if you're at the bottom row or the top row, or yeah, you go all the way off the row, like what happens? So if you go all the way off the row, that means that nothing in that row, that means that there really is only the top matrix. I actually think if you go all the way off the row, that means that everything to the right, everything is in that row is too large. So everything below it is gone immediately. And I guess the things above it could be, I think everything above it could be the matrix and everything below it has to go. So what do you end up with? You end up with what happens. So let's think about that case. The index is too large, so the starting row stays the same. The starting column actually shouldn't change. I want to say you could take this modulo, you could take this index modulo the number of columns. Yeah. Yeah. Because that would actually give you, this iterator would give you minus this initial column. If it was this initial column, it would be this thing plus s column. You would subtract this begin. You'd have the starting column, and you'd also have this. So the initial column plus n columns is this thing plus the number of columns. So if you take this modulo number of columns, you actually get this row begin. You subtract the row begin, you actually get the starting column. You get the right starting column. How about, and the starting row is the same, starting columns, the right matrix ends up being just above. The count row, number of rows is right. Yeah, it's the same thing. That doesn't change. The number of columns, so that's interesting. That's going to be actually the same deal. Modulo n columns. No, no, this is actually fine. Index is going to be this initial column plus n columns, which is, it's going to be the starting column, the index minus this matrix begin is going to be start column plus n number of columns. So this is going to be 0 plus 1, which actually is wrong. So you do want to do modulo n columns. So this will go to 0, the index. This is the start columns plus the number of columns plus 1. What happens then? It's actually not modulo the number of columns. That's also confusing. Oh, this is so confusing. This is so confusing. I keep thinking about it like it's the 0 index is the starting row and the starting column point, but it's not. Like all of this is supposed to be relative to a starting row and a starting column. However, it's really hard to think about it like that. It's so hard to think about it like that. Because this could be like a matrix in the middle of, it could be just like a square in the middle of like a huge matrix that a lot of things have been sort of, we're not considering the rest of the matrix, we're just considering this little rectangle in the middle of all of it. So it all has to be relative to that starting row, starting column. So if you just take modulo a number of columns, that's not going to make any sense in that context. Again, this is definitely way too much thinking and messing around for an interview. I think once I finally get it, I'll have like a clear, concise way to understand it, and then I can kind of like go to it again next time. Cool. So let's start again. So that starting column is going to be that index. If that's off the edge, I want to say something like you know what I want to do? I want to bound the starting point and the yeah. All right. All right. Let's do it this way. I have an idea. I know what to do. I'm not even sure if this is all as correct as it is either. But basically, I'm going to write a subroutine that just checks that these matrices are within the bounds of the previous matrix. That's really what it's got to be. Just have to be a sanity check on the previous matrix. And then you have another sanity check here, but this kind of doesn't matter because you're sort of given the matrix anyway, so this don't really matter as much. But the matrices that you're about to consider, that those matrices are sort of bounded within the original bounding the larger matrix. That's what I want to write. That's why I just wrote a simple check for that, rather than trying to like finagle with I don't know, modular arithmetic, whatever it was I was just trying to do. So this makes sense. So let me just think again. So the starting row for the right matrix is going to be the original starting row. The starting column is going to be whatever this index is the, yeah, even in the context of a larger matrix, is still the same index. Number of columns is the same idea, or number of rows is the same idea. The number of columns is a little bit more involved. So we get the starting column plus the number of columns minus that index. So sort of considering the larger matrix, and then add 1. Because that column at the index, we do consider that column for the right matrix. Actually the left matrix, the number of columns is exactly it's the same thing except, well, it's slightly different, right? It's actually the index minus the starting column. Yeah, actually, I don't think you need to start. I don't think you need to subtract 1 here because you're going to remove the starting column already. Alternatively, this is the number of columns minus this whole thing, which would be, yeah, which would be this. These would cancel. This is negated. This is in oh no, you do have to subtract 1. Yeah, so I was right. Okay, I was right. Yeah, alternatively, it's number of columns minus this thing, which would be this. This is negated. This disappears. This is added. Subtracted. This is subtracted. Okay. Number of rows is right. Starting column doesn't change for the left side. Starting row is exactly, it's just below this one. And the number of rows, number of rows is total number of rows minus the other matrices number of rows, which is just the count row minus 1. Okay, so I think I could figure this out sort of quickly on the spot if I had to do it again in the future. You basically just consider like the duals. So the number of columns on the right and left are going to be something of a dual of the number of columns, and also the number of rows on left and right are something of a dual. So if you add them together, they should be the number of rows minus 1 for the rows, and then the columns, you should add them together to get the number of columns. So if you do so, you'll get this cancels with this, and with this. Kind of wondering why we add 1 or subtract 1 over here. Not sure that you should do that. So if you take the let's say the starting column is at index 1, so the first 2 columns, and then the index is like 4, so it's the first 5 columns. So you do 4 minus 1 gives you 3, is 3 columns between the fifth column and the second column. This seems to be correct, that well, no, you subtract 1 because you don't include the 5th one, right? So it's really it's more like index minus 1 minus columns, yeah, because you don't have that index value is actually gone on the bottom left, right? That's why. Okay, and then it's actually appended on the top right. So anyway, we do want to check a certain. We have to do another routine, so it's called inbounds, which is interesting because now we have these two a subroutine that contains a subroutine. I was kind of wondering when that was going to happen, when exactly that was going to happen. We'll say int row, int column, and then int number of rows, int number of columns. And we just want to check that return it's got to be, so starting row less than or equal to row, and which is and so the row is greater than or equal to the starting row, and the row is less than or equal to the starting row plus the number of rows, or this starting row plus the number of columns, and the column is greater than or equal to the starting column, and the column is less than the starting column plus the number of rows. That doesn't make sense. I did that wrong. Right. So this means that we're within the original matrix. That's all this means. And so that would be right. we don't actually need these. These are given already. That the row is less than the starting row plus all the rows that are in the matrix that we're considering now, and the row is also greater than or equal to the starting row, right? So this just means that the starting points are not out of bounds. And then we also need the rows and you have more than this too. Call new and number of rows and new number of columns, and the row plus the new number of rows is less than the starting row plus the number of rows. Do you need row to be less than this and row plus this? If this is true, does one of these imply the other? Yeah, if this is true, that implies that this is true, right? So you actually don't need to check that. You just need to check this. Right. Okay, yeah. So the row and the column are at least, you know, in the right spots with regard to the matrix, and adding rows and columns is still going to be within the matrix, right? It's like a very interesting bit here, but so we could say bool m1 or ml or mr is going to be this value, and then we're going to say, actually we could even do okay, I got it, even better. I wanted to preserve the kind of what do they call that? I wanted to preserve the what's that called? The early terminating behavior here. Yeah. And so inbounds of row column. So really it's fine. It doesn't really matter that much. That's fine. Oops. I just missed like one character here and there, or I tend to. So, okay, yeah. So the inbounds check, and then you have the recursive check, and then you say ML or MR. Okay, I think this is what we want. Like I said, kind of involved. Now, with these inbounds checks, I think that handles all of the sort of degenerate cases as well. So these will just automatically be false, and you won't even bother executing on the sort of the degenerate matrices. I think from here we can then just take return this recursive search, and we would have row, or yeah, 0, 0 for the row and column initially, number of rows, number of columns, and then recursive search is the function that we execute on. Let's see if it compiles. Oh, missed that. That might be why. I was wondering why I didn't get a the tab wasn't working as I was expecting it to. It's probably over here too, yeah. Kind of did that in a few spots, huh? Oh. That's my mistake. Output false, expected true. Nice. Nice. Ouch. That's always good. It's always good when you spend, I don't know how much time I spent on this and it's wrong. That's fun. That's fun. Alright, so what should happen is this is the test case that we have over here. We should get 0, 1, 2, 3, 4 is the 0, 1, 2, 3, 4 is the yeah, 0, 1, 2, 3, 4 is the, and 0, 1, 2, 3, 4 are the number of row, the row column, the number of rows, number of columns, and the indices. So the count row is going to be 5 minus 1 minus 2. So the initial rows here. Step row is going to be 0 plus that, right? Step row, initial column is going to be the step row begin plus the starting column. So that's the initial column. And say, okay, take that initial column and then initial column plus the number of columns. Look for the target. We should find greater than or equal, lower bound, so greater than or equal. So we should find 6 here. And we do the shenanigans with the matrices. Let me just do a debug message here. So that's kind of what we would expect. The initial column is always something that we can always exists, I guess. It's something we can always dereference. So 6 is initially what we get, and then this matrix we should find in this matrix, the left side or the right side, I guess. What do we get for ML and MR, I guess? Matrix left. Let's see. Matrix left 0, matrix right 0. So these both immediately fail. And I wonder why. I don't think we actually get these recursive calls. I think it fails the inbounds checks. I want to say this fails the inbounds checks. Okay. Well, we can say, and that's crazy. I used to be really, really, really insecure about, I don't know if I should share that. I used to be extremely insecure about being like, I guess I want to say attractive enough or good enough as a man. And that has left me. That has left me. I don't know why I had such, I remember thinking that a few times, like being really insecure about it, really uncomfortable. And then, yeah, I don't know why I felt like that. I don't know. It's a really weird thing to feel, I think. I guess it just seemed like, I think I know why. It's probably because everyone else I know or knew, they all would date and get together with somebody. Whether or not it was right or wrong, I had no idea. All I knew was that people were doing it, and that was something I wanted. However, it's not that simple, right? Like when you do something, there's like a beginning and an end. There's like sort of a state change, and then like the world's a different place after you do something, and it may not necessarily be good that you get together with somebody. It may not necessarily be a good thing. You might think it's good, but it may not necessarily be good. Or vice versa, not getting together with certain people or quote unquote someone you might think is a bad thing, but actually it might be a good thing. Like if you're wanting to get into something, it may be better that you didn't. Something like that. Might be sort of God's will that you don't. Yeah, those insecurities. They were, I felt them a lot when I was younger. Don't feel them now, let's say. I'm actually kind of recovering. Sort of recently, I'm starting to really recover from that kind of thinking, that kind of approach to things. Anyway, so yes, it looks like the inbound checks keep failing, or they are failing. That's not correct. The row left and row right. These are the row is greater than or equal to the start row, which it is on the left side. Yep. The column is greater than or equal to the column on the left side, definitely. Starting column. The row plus the new rows. So this row plus the new n rows. Oh, that's going to be less than or equal to. Aha, that might be what I'm failing at. Yeah, that might be why. Yeah, I guess we will put in. Let's say row bound. You get in kind of funky territory here with so the starting row plus the end rows and this starting column plus the end columns is sort of the column bound and the row bound. The row plus the new number of rows actually should be equal to the row bound, and same thing, or could be, it's got to be less than or equal to the row bound. However, the row itself should be less than the row bound, same thing column. So it's a little bit confusing why that would be the case, but I think that's what I missed here. Yeah, there we go. So now inbound on the left. Inbound on the right matrix should still be true though, right? Inbound on the right we have okay. Let's actually print the values then. Start row right. Oh boy, this is a lot. This is a lot of debugging. A lot of time is really the issue. Start row, start column right. I don't know what's wrong though, you know. New row right and rows right. And columns right. And 0, 1, 2, 5. Okay. And we can also print a line for just the starting row and the starting column and the number of rows and the number of columns. Okay. Oops. Alrighty. So starting row on the right side would be 0. Starting column is the first column, right? It's this one right here, right? This row, this column. The number of rows is 2, right? Correct. Number of columns is 5. 1, 2, 3, 4. No, the number of columns should be 4. Why do we get the number of columns to be 5? I thought there was a +1 there, but I guess not. And consequently, I guess I was right the first time then. So the S column is the start column, 0, plus the number of columns, 1, 2, 3, 4, 5, minus the index, which should be 1 here. Oh no, yeah, 1. That would give you 4. You know why there's a +1 there? It's because the number of columns pushes you over to this index. Yeah, it should be columns minus 1. And then the number of columns, if you take this should be the number of columns minus this whole thing, which is going to be this inverse. Okay. Yeah, a little confusing, but I think I still got false, but it's a little bit better. So yeah, this right side was 4 columns now. 1, 2, 3, 4. Okay. And then now can actually do the left matrix. So hold on then. So they're initially left and right here. Well, right. So all these matrices should be inbound. Left and right matrices should be inbound. So we don't have to worry about that anymore. I don't really need this anymore either. Well, we can do the right and we can do the left, and then we can do and then it recurses. So we do the left. Thinking I probably should have written a subroutine here or something, but that's okay. What does that look like? Really don't need this anymore. Oh, it's so itchy. Gosh. Okay, before we enter, and then, I don't know, I don't know if we'll be able to track down the left and right. Because you gotta actually recurse before, so these are kind of, it's always gonna be false in all cases anyway, if it's not true, right? You don't get it true. So, what's 6 and what's 7? What's that? Where's that coming from? Debug, okay. So we got 6, there's a right and a left. Process the left one first, and we get 7. So, yeah, on the left matrix, we actually just return false up here because we don't even bother, because we have, well, no. Yeah, so on the left matrix, what's going to happen is this is fine, but when we recurse, oh no, wait, yes, no, wait a second. What is going on? There's a right matrix, there's a left matrix. I think this left matrix fails. Oh. Oh, it does. No kidding, this left matrix just fails immediately. It's in bounds, but when you call this, you get starting row, starting column, new rows, new columns. Oh, got it. That's really confusing. It's actually, no, this is wrong. Really the inbounds check is what you want. This sanity check just happens up here, really. There's no sanity. This you don't want to run this one. The inbounds check is the sanity check. That's it. That's the only this doesn't make sense because the starting row and the starting column can be way different from the number of rows, number of columns, right? So that's probably, yeah, that makes sense. If the number of rows and the number of columns is negative, then obviously you can, that's maybe a sanity check you want to have, but I think that's only one. So you've got a degenerate. But as long as you're inbounds, should be fine. I think you do still need this, but that's kind of interesting. Oh, we got it. There you go. Yeah, so there were cases where, right, these degenerate cases that you need to prune off. I thought you might have those, but the inbounds check over here is sufficient. So this is kind of involved, this question. It's kind of something. This inbound check kind of ended up being kind of important. And a lot of pieces to this. I don't know if this is correct. So right, you get 6, then you get 7, or no, 6, 10, and then after 10, you're kind of in degenerate cases, I think. I think once you get 10, everything's eliminated after that, so it's degenerate cases. And then you have 7, which you eliminate below, and you have again degenerate case above, I suppose. You're sort of already reduced to this matrix. So 7, you get rid of this portion, and you're looking at 4 is gone too, so you're looking at just 5, and then you get 5 and return true. Yeah, let's do another case, or do some other cases. Let's do one where we don't have 5 in there. Yeah, let's do 5, and we'll do this 6. I think there could be duplicates, right? Let's make this 6 a 7. Well, first off, let's make this 6 a 7. Let's see if we still get the same answer. We do, and then we can actually take this 5 and make it a 6. And then the 6 underneath is a 7, right? There's multiple 7s here. That's okay. So don't find 5 on the last one. Okay, that's good. Now I don't know. Let's see what happens if these other test cases. Kind of a lot of cases to check. Invalid test case, not a valid test case. All right, how did we do here? Not a valid value of type integer. Okay, I think that's this. Wait, which ones we're looking for here? Which test cases are invalid now? Okay, these are all correct. That's interesting. We can also remove this debug message now. I'm gonna just comment it out because I just don't want to see all this extra output here. I just want to see expected 1, 2, 3, false, false, false. So these two test cases down here are actually real test cases. Okay, that's interesting. How about that one? True at the bottom. Interesting. The singleton works too. And then how about this one? Okay, that works. A lot of test cases to go through here. I'm fairly certain we have it correct, but you kind of just want to test these because there's sort of just so many different possible ways this can go wrong. Okay. And then 1, 2, 3, I guess is. So this doesn't have, that doesn't work. Okay, no, it's not a valid test case. But this, I think is a valid test case. Yeah, okay. So for 3 and 4. Okay. All right, I think we got it. I'm afraid to go for it, but I think we'll go for it. Hey, we got there. Nice. Whew. No kidding. Oh, dude, that took a really long time. That took a lot of time. Wow. No kidding. Gee. So, about that. Interesting. Is this not logarithmic time? I think this is log of m plus log of n. I think the reason why this is so slow is because this has a lot of overhead involved, but this is logarithmic with respect to the whole matrix. Yeah, as you saw, each iteration cuts the matrix into basically into half, and it eliminates half the matrix just about. You end up with these two matrices, one below, one above, matrices to look at, and everything else is eliminated. And there's sort of like a mirrored. You can kind of prove that it's about roughly half of the elements. It's a little bit more than half actually get eliminated each time. However, the constant's pretty big, I think, involved. So yeah, pretty interesting. I like this approach. This is just the only thing I don't like is how much the sort of time and effort, how many different like pieces were involved. I bet there's a simpler way to do this. It's just, I bet there's a simpler way to do this. It's just, gosh, it's just. It's kind of hard to think your way through all of this, and make sure you get all of the right, all of the edge case boundary cases correct, and also all of these new values, these new input values correct. I don't know. It's just kind of challenging. Like there's just a lot of pieces involved. Ultimately, this is sort of the way it goes, I guess, or the way that I end up doing it, but. By no means did I do this quickly, right? Like this, I coded this up. It took probably over an hour. I think. How long have I been streaming? Since 8:30, 2 hours I spent on this. That's really kind of a lot. Yeah, it's a lot more than I was expecting to spend on this. This feels like a question I should probably come back to, I think, at some point. Like, I don't know. I don't think I could code this up in an interview setting this quickly. Or not this quickly, but I don't think I could code this up in an interview setting where this would be like reasonably quick. It feels like this would take me a really long time, just because this piece alone takes a while, and not only does this take a while, but it's extremely error prone. Like I had to run through a lot of test cases. The inbounds check also is kind of involved somewhat. It's a really simple approach ultimately. However, I definitely you definitely got to question this. Definitely got to question this. How quick it is to put it together. I don't know. I don't know how I could do this faster the next time I see it. Well, the next time I see the question, the problem, I'll know it, the answer. Oh yeah, let's look at this, the discussion. But yeah, that's a divide and conquer. Yeah, it's 4 lines in C, 6 lines of Ruby, 7 lines of Python, 1-liners. Are you kidding? 2 solutions. Binary search tree. So a lot of these folks did O of m plus n, but this is there, yeah, there is O of log m plus log n. I have it coded up. I did it. Answer to your question is no. What? I thought mine is O of log m plus log n. You know what I just realized? Mine is O of m plus n. Yeah. I didn't need to put that much effort in this, did I? Yeah, in the worst case, what can happen is, no, I'm pretty sure you eliminate half of the matrices, elements of the matrix, no matter what. Although, yeah, I'm pretty sure. No, I'm pretty sure my approach is O of log m mn. Maybe I'm crazy here, but I'm pretty sure it is. Craig nice explains the lower bound of m times log of m over m, lower bound where m is the smaller and m is the larger of height and width, and log is the normal logarithm except doesn't go below 1. There's a lower bound on this? I don't think that's true. I don't think so. Maybe it is non-optimal. I'm pretty sure it is though. We're gonna read this right now. First notable solution, elegantly simple. Query in the bottom left of the not eliminated area, hitting one row or column at a time. It takes O of width plus height time, where height is the height of the matrix and W is the W of the matrix, width of the matrix. Find when it's approximately square but not optimal when the matrix is much wider than it is tall, or vice versa. Line at a time. Always query in the bottom left of the non-eliminated area. Eliminating one row or column at a time. So the bottom left row, I guess. So you do the bottom row. O of width plus height time. H is the height of the matrix and W is the width of the matrix. I'm actually not sure how you do this. Non-optimal when it's very tall or very wide. But you also have, but how do you get O of W plus height? What do you mean you do? Oh, I think I understand. If you start at the bottom left, if it's too big, and so you traverse from left to right from the bottom left, right, just one item at a time, and until you get to you know, I guess until, right, so you sort of do like an upper bound on the bottom row. And then you say, okay, go up to the next line, and that's a smaller value, and then you can go I guess well actually one row or column. Okay, I think I understand. So if you if you do the top row, go all the way to the right, and it's not in there, then you can go down and you can go to the left some. I guess until you're smaller than the value you're looking for, and then you go down again, and yeah, I think I got it. So if you go left to right and you don't find it, all of the values that are below what you just looked for, they're all going to be larger. And so you can start from the top right, and you can go back. No, not like that. No, how do you do this? You would do, I want to say, like, you got to find some point. So if you start at the bottom left, you go to the right. Like the first value might be too large. Value above it. If the first value is too large, the value above it, if that's too large, then you keep checking. All right, so you kind of keep eliminating the rows at the bottom until you find something that's not too large, and then you move to the right until you've hit a point where it's too large, or you find it. You hit a point that's too large. Now you go up again, and you keep going to the right again. Right. Yeah. So you make this kind of zigzag from the bottom left all the way to the top. Yeah. Okay, that makes sense. I've actually seen that solution before, although I forget it every time. Whenever I see this problem, I always forget that solution. But that's right, like the most elegant, simple solution that a lot of folks submit. So you say, however, it's not optimal in certain cases. I would argue it's not optimal, period. But anyway, divide and conquer. Queries the center of the rectangular area to be searched, eliminating either the upper left or bottom right quadrant, then divides the remaining valid areas into two rectangles and recurses on those. Okay, so that's what I did, and I thought that was correct. Queries the center of rectangular area to be searched, eliminating either the upper left or bottom right quadrant. Well, you can eliminate both at the same time, simultaneously. Interesting recurrence relation for its running time, assuming the asymmetry of the search areas doesn't affect the running time. To me, this looks like a nice efficient relation when you actually solve it. No, you can't apply the master theorem. You see that it's not. Current relation solves to Fibonacci. So the divide and conquer algorithm takes O of width times height raised to the 0.7 time, which is O of width plus height 1.4 when width is approximately height, which is more than line length times O of width plus height. A variance algorithm divides the remaining area into three rectangles. It also requires more than linear time. Although its recurrence relation is easier to solve, more careful analysis shows this approach is actually optimal. Whoops, see the comments below. Oh. Okay, I was gonna say, I'm pretty sure this is logarithmic. This one, the one that I did. Multi-binary search, binary search of each row and column, depending on which is longer. Yeah, O of B log or right. Non-optimal height is about the same as the width. In case the running time reduces to width plus height times log width plus height, which is less efficient than line of time. Algorithm is not optimal even when width is a lot larger than the height, or height is a lot larger than the width. Too bad, it's otherwise an optimal solution would be just to switch between multi-binary search and line of time based on how tall wide matrix was. Right. None are optimal. Takeaway so far keeps giving non-optimal answers to this question. Don't plan as optimal if you search around. You find plenty of ones. More complicated than it appears to solve the issue. I'm going to solve the problem. I'm going to prove. Optimal usually proves some lower bound on the amount of required time. Optimal, an algorithm that achieves the time bound. Lower bounding adverse diagonal. Imagine you are an adversary that controls the entries of the matrix being searched. I don't want to read too much about this. What is this lower bounding adverse diagonal? We'll get back to that in a second. Upper bounding. Be wary that the solutions you'll find online are mostly not optimal, taking either O of b times t plus equals O of width plus height or O of b log b plus t time, b times t time. After I solved the problem, I went looking, only found one person who found the right bound. Plus 1 confidence points for Evgeny Kluev. He said that this is optimal, but how did he? I was gonna say, yeah, I'm pretty sure it's logarithmic log of width plus log of height as well. Not necessarily this one, but if you split into two, you basically eliminate two sides of the matrix. And the reasoning I gave is true for every because if you recurse on two submatrices, right, then the next iteration splits into yet two more matrices, and half the elements have been eliminated, and no matter what element you select left to right on the row, half the elements in that matrix are eliminated, and then you just end up with the degenerate cases. But in theory, you can, in large, asymptotically large numbers, that shouldn't matter. You shouldn't worry about the extra constants from the smaller test cases. Yeah, and then obviously you're getting two calls to execute on but those calls are operating on both on a fourth. It's two calls on a fourth of the original matrix, right? So each call has a fourth of the, so it should work out, right? You could imagine it being one call on half of and that's logarithmic, but it's actually less than half each time. You could even code this up. I don't know if you can code it up as but yeah, I'm pretty sure two calls on a fourth of the size. I'm pretty sure it's logarithmic what I wrote. And it's log of m times n, which then you can reduce to log of width plus log of height. And then that's also optimal in the other cases too. Maybe I'm crazy, man. Maybe I'm just, I don't know. I kind of want to like publish something somewhere and be like, hey, you guys need to think about this. Somebody tell me I'm wrong. Somebody tell me I'm wrong and tell me why. So he's saying that there is a tight lower bound. I don't think that's true. I don't think that's true. He explains this lower bound. I don't think that's true though. Imagine an adversary who controls the entries of the matrix as it's being searched. You can delay choosing the value of a cell. Oh, no, I think I'm wrong. I'm sorry. I take it back. No. Sorry, I'm sorry. My algorithm is not. I made a mistake. It's not, I take it back. It's not always log of width plus log of height. And I actually said that earlier. The reason is that you could end up eliminating a single row every time. Yeah, no, it's not. No, it's, or yeah, no, yeah. You end up eliminating a single column and a single row every time. You don't know. I'm sorry, I take it back. You don't always split. You don't always split it into two pieces. I was wrong. I was wrong about that. No. I actually don't know what the running time then is. Shoot. Never mind. Shucks. I think my algorithm is. I think it actually is this lower bound. I think it's optimal, but I think it is this lower bound, depending on the worst case. I think it means this lower bound. Yeah. I think it degenerates to that lower bound in the worst case because you do a basically every column, you eliminate one column at a time, each time performing a binary search on the row. Yeah. And it degenerates. It degenerates when you're when you only eliminate one. What do you call that? When you only eliminate one element, like the first element of the row each time, which you can imagine, which I think is basically what he's describing here. And yeah, because that's one of the matrices doesn't even get processed then. And it's not that one of the matrices doesn't get processed, it's just that excuse me, it's just that actually, I think for my case, you'd go all the way to the right every time for each row that you process. You go all the way to the right of what's left. Yeah. Yeah. And so it reaches the lower bound. Okay. That's interesting. Take it back. I take it back. It's not true that no, in the worst case it doesn't always eliminate half. I forgot about that. Okay. I still think I have a pretty good solution though. But yeah, the divide and conquer is optimal, right? Pretty interesting. Let me get going here. Gosh, I thought I was so smart. Answer is no. Pretty good. Pretty good. No, this is wrong. This is wrong. Yeah, more careful thought. You realize it's not. It's got a -1. Yeah, more careful analysis, you could realize it's not. That's what I did. Anyway, I don't think this analysis is correct though. Maybe I could be wrong about that too. But I don't think this is the right analysis here as described. Yeah, you would have, you could, if it's, let's say if it's relatively balanced, in other words, most of the time your search, your binary search is not going to like basically degenerate, which it is most of the time. It won't be degenerate. Then the average case is logarithmic. If, however, you have sort of a bad test case, in the worst case, then it degenerates to the lower bound. I don't think the divide and conquer, depending on how you write it, gives you a worse test case. Worst bound. Yeah, he updates. Okay. Anyway, all right. Let me get going. Pretty interesting question. I probably should read further down on his notes, but really interesting. I mean, that was a good question. It's kind of a classic question. I've seen it a few times. I went with a divide and conquer. I thought I was super clever with the divide and conquer. So TLDR with this question, really, it's if you see this, you kind of just want to do the O of width plus height solution. By the way, I've seen this question so many times. There's a few things to say about it. One, this is the first time that I wrote the divide and conquer solution. I think the first time I saw this, I came up with that kind of staircase solution, that O of width plus height solution. Obviously, for obvious reasons, like most places will accept that solution. If you could even code up the divide and conquer in a reasonable amount of time, I wouldn't recommend even trying, because as you saw, it took me forever. I've seen this so many times. I've seen this when I was at university. So we're going back like 6-7 years ago when I was attending university. I had this question on one of my exams. This is a very classic question, classic problem. Yeah, I had this question on one of my exams, and that particular class, I had done so well in that class up to sort of the ending, the last part of the last few, I guess the last exam, we'll say. I did everything I could, did everything as well as I could, and pretty much had like 100 sort of in the class. And then I bombed the last exam. But the way the grading works, I think they drop your worst score, something like that. And I believe I still got an A in my algorithms class. I don't remember what score I got, but yeah, I remember. I'll never forget that class. That was such a hard class. That was 6-7 years ago. I was looking at problems like this, and even now I'm still kind of struggle with solving it. I know a lot more now though. I'm a lot better prepared. But yeah, I can't believe I was like 20, 21 years old, 22 years old, something like that. That was a long time ago. Yeah, this was a hard question. This was hard. I remember that was the first time I saw it was on the exam, and I was like, I don't know, I had to really sit and think about it. But I think I did get that something like that staircase solution, which, yeah, you can start in the bottom left and move. And you say, okay, this is too big, so go above it. If that's too big, go above it. That's smaller, so then go to the right until you find something that's too big, and then go above it. And then that's it. But if that was smaller, then you can go to the right, and then so yeah, you could staircase from the bottom left. It's very succinct, really elegant solution. However, not optimal in all cases. To make it optimal, though, by the way, is you just use a binary search to find the your entry point. And you could, what do you call that? You could transpose the matrix, I guess. In other words, if m is greater than n, so you could, instead of going row by row, you go column by column. So instead of the bottom left, instead of searching the rows, you could search the columns. And then, so binary search on the column, and then do the same thing. You say, okay, I want to go to the row. If that's too big, oh no, bottom left. You go up, so it's smaller. You go row by row. If you go bottom left column, you have to go to the right. No, you would actually, I'm thinking, how can you do this? You would go, you can go column by column, and I guess it would be in the bottom left would be the top right column. Or yeah, the top right of the column. No, that I actually don't know. I don't know if you could do this if it's, no, you can't make it optimal. No, transposing the matrix doesn't work like that. Well, actually, if it's very wide in the right direction, if it's a large number of columns, then I think it's optimal still if you do the binary search left to right. Yeah, you just have to use the binary search going, yeah, to the right, left to right, and then if there's a very small number of columns, a very large number of rows, then actually you would do a binary search on the first column to find the starting point. And then you would move to the right, and that would be larger. Excuse me. In which case, I guess you'd want to do, I'm actually not sure. Moving left to right, you'd want to go to a spot that's where it's smaller, right? You actually want to go to the left where it's smaller. So actually what you would do is you'd binary search on the rightmost column, and then you go to the left, and then binary search again down to the bottom, wherever it should be. And so that's at least as efficient as the width plus height solution, and it's also at least as efficient as the sort of binary search line by line solution. Yes. So you can slightly modify that to make it optimal too. And then obviously the divide and conquer is also optimal. So pretty interesting problem, really interesting problem, really interesting problem. But yeah, I remember solving this. I remember seeing this on an exam when I was at university many years ago. Wow, do you know what's crazy? My sense of self, my sense of like confidence, has been so rattled and just broken over the years. I mean, I've just become like an utterly broken person over the years. So I'm thinking about it. It's like this problem, I don't know, it's like not that big of a deal. Like I'm thinking about, what I learned over the years as a software developer, and like learning this problem way back when and things of that nature. Like I don't even know what to think anymore. The world is such a strange and confusing place, I guess, something like that. Kind of just had this moment of like just something of a trip. I don't know, man. I got like bounced around all over the place in my life into so many strange positions and uncomfortable situations that I can't even, like I said, I don't even know where I am anymore. So sort of like I have to kind of look back at all of this stuff that I did. I don't know. This question kind of gave me like something of a blast from the past, and so there's so much to think about my life. There's so many just things. But that is a big thing, or was a big thing, is that I had this like, I mean, more recently, if I wanted to get hired as a software developer, I have to be able to pass these exams, these interviews, and it had been extremely challenging to do that. They're actually not that hard. They're really just, you kind of just got to study the algorithms a little more. Really shouldn't take that much time, actually. And then worse is, working as a software developer for a software development company, some company that builds software, that getting a job. When I was younger, it seemed like it was impossible or something. Like it was just so beyond me. And the reason was that they would ask for certain skills, like certain experience that they wanted to see on the job descriptions, and I didn't have that experience. And it was like, where am I going to get, if I need a job tomorrow to pay the rent, where am I going to get a job? Where am I going to get 3 years experience of whatever it is they're asking for? And then realizing that what they're asking for is kind of meaningless and irrelevant, that all you need to do really is build a project that uses that technology, which shouldn't take that much time. If you need a little bit of guidance, however, then you can just apply for those jobs and just show them, hey, I have this project and I'm familiar. Then there were things I didn't know too. So such small, simple things like setting up your own, like getting hosting for an IP address for a machine, and even getting a remote machine somewhere where someone else basically has your files. It's like Heroku, I think, was one of these sites, and that was something that I didn't understand or realize either, is that it's actually really easy to start coding websites and building stuff online. It's like very easy, very doable, very inexpensive. For some reason, though, it seemed to me like it was this impossibly difficult task, because actually, if you did try to basically put your own data center together, it requires a bunch of different things that are kind of really difficult to do on your own, I guess, like as just an individual. One of those things being having 2 different static IP addresses for 2 different DNS servers, and a third static IP address that if we actually serve and then a machine that you actually serve your website on. All 3 of those things are actually very expensive if you're going to like buy property to get the static IP addresses. However, if you get hosted on someone else's system, which is basically a farm that does nothing but hosting, then it's extremely efficient and inexpensive. like we're talking like 1,000 times, or 100,000 times, something like that. You know, like $500,000 for 3 houses, or no, excuse me, $1.5 million for 3 houses, or $5 for a hosting service. So yeah, almost 1 million times really would be on the order of about 1 million, which is a lot, which is really a lot. Gosh, and yeah, I mean C++ is gigantic too, but you don't need to have that much skill in C++ to build something. And same thing with really all the software that you deal with. You really don't need to be that skilled. You want to have some degree of skill, but it doesn't need to be that extreme. Not necessarily enough to do most things. Yeah, I don't know, man. I don't know. I think about my life, and it kind of gets me a little bit like, gosh. But yeah, this question, I remember there was, wow, I had such a bright future ahead of me. I guess is how I would express that. I had such a bright future ahead of me. Not that it isn't still bright. You know, whatever it is God's will, right? Whatever is done is God's will. Obviously, sins. That's kind of a confusing thing to think about. You know, it's ordained by God because He has providence over everything. However, you still have your own control of your own choices. You're still morally culpable. So there's a certain dichotomy there, but you know, God kind of knows what you're going to do before you do it anyway, right? It's like in the same way you know that, you know, if you put food in front of a dog, he's going to eat it, right? Like it's the same thing. God knows what you're going to do for the most part. Gosh. I think. I'd imagine he's an infinitely knowledgeable, so he would know. Anyway, okay, let me not meander about here. Let me get going. Yeah, really interesting question. Very classic question. Really interesting one. The solution is pretty straightforward. The linear O of width plus O of height solution is a pretty good one. Excuse me. Yeah, that binary. If you modify that with a binary search, it actually makes it a lot faster. What you end up with really is the minimum. So the O of the height plus the width gives you the maximum of the height and width. If you take O of if you do that logarithmic thing, then you actually end up with you get O of the minimum times the logarithm of the maximum. Yeah. Yeah, you can optimize on that. And then I think the divide and conquer, you end up in the same scenario. Actually, it's not quite as good because it could be. It's actually not necessarily. Yeah, well, you could modify the divide and conquer such that it is the same. Where in the same way that you would change the binary searching, I change the algorithm depending on which one's longer, the height or the width. You could do the same thing with the divide and conquer approach. Okay, alrighty. Yeah, so thank you again for watching. I appreciate it. I will talk to you all soon. have a good rest of your day. This is something. This question. This is something. Okay, I'm out of here.